Welcome to the video on frequency distributions and histograms. In this video, we'll start to talk about how to create a table or a graph to summarize a set of data. But before we get further into this video, we need to talk about the meaning of the word frequency. So what is the frequency of a value? The frequency of a value is just the number of times that the value appears in the data set. Let's look at some examples of frequencies. For our first example, let's imagine that I've asked 5 people how many siblings they have, and I recorded these 5 answers. 2 people told me that they have 1 sibling, 2 people told me that they have 2 siblings, and 1 person told me that they have 3 siblings. This answer of 1 appeared 2 times in the data set. This answer of 2 appeared 2 times in the data set, and this answer of 3 appeared only 1 time in the data set. Since 1 appeared 2 times in the data set, 1 has a frequency of 2. Since 2 appeared 2 times in the data set, 2 has a frequency of 2. And since 3 appeared only 1 time in the data set, 3 has a frequency of 1. So we have 2 1s, 1, 2, which is why this answer of 1 has a frequency of 2. We have 2 2s in the data set, 1, 2, which is why this answer of 2 has a frequency of 2. And we have 1 3 in the data set. That's why this answer of 3 has a frequency of 1. The frequencies of all of the different values have to add up to the number of values in the data set. And we can see that's true right here because 2 plus 2 plus 1 equals 5. And we have 5 values in the data set. 2 1s, 2 2s, and 1 3 make up 5 different values. Let's look at another example of frequencies. In this example, let's imagine that I've asked 5 people how many classes they're taking this semester, and I recorded their 5 answers. 1 person said that they're taking 1 class. 1 person said they're taking 2 classes. 1 person said they're taking 3 classes, and 2 people said they're taking 4 classes. Since this value of 1 appeared 1 time in the data set, 1 has a frequency of 1. Since this value of 2 appeared 1 time in the data set, 2 has a frequency of 1. And since this value of 3 appeared 1 time in the data set, 3 has a frequency of 1. And since this value of 4 appeared 2 times in the data set, 4 has a frequency of 2. And just like before, all of these frequencies add up to the number of values in the data set. 1, 1, 1, 2, 1, 3, and 2 4s make up the 5 values in the data set. Now that we know what a frequency is, we can talk about how it's possible to create a table to display the frequencies of the values in a data set. A table that displays the frequencies of all of the different values in the data set is called a frequency distribution table. We'll talk about how to create the frequency distribution table. A frequency distribution table has 2 columns. The first column is the X column, which shows all of the different unique values in the data set. It shows all of the different values that appeared. And the other column is the F column, which shows the frequency of each value that appeared in the data set. We'll go through 2 examples of creating a frequency distribution table. First, we'll create a frequency distribution table of our first data set. So let's go back to this data set in which we recorded these 5 answers. We need to have 2 columns, which are the X column and the F column. Let's create the X column first. Remember that the X column just shows all of the different values that appeared in the data set. The different answers that appeared in this data set are 1, 2, and 3, because this data set is made up entirely of 1s, 2s, and 3s. So that's why those are the 3 numbers in the X column. We also need the F column, which shows the frequency of each value that appeared. So 1 appeared 2 times, because 1, 2. So 1 has a frequency of 2. 2 appeared 2 times, 1, 2, so 2 has a frequency of 2. And 3 appeared only 1 time, so 3 has a frequency of 1. This column shows all of the different values that appeared, and this column shows the frequency of each value. So here we have, so what this table shows is each value and the number of times that that value appeared. To create this table, you just have to list all of the different values in the X column, and then you have to go to the data set and count how many times each value appeared. Let's look at another example of a frequency distribution table. Let's go back to our second data set. This is the data set that shows the number of classes that each person was taking. Remember, I asked 5 people how many classes are you taking, and I recorded their 5 answers. These are the 5 answers that they gave, and we have to, if we want to create a frequency distribution table, we have to start by creating the X column, which shows all of the different values that appeared. In this data set, we have a 1, a 2, a 3, and a 4. So that's why these 4 numbers are in the X column. Now we have to create the F column. So we have to count how many times each of these values appeared. 1 appeared 1 time. So 1 has a frequency of 1. That's why 1 will go here in the F column. This is just saying that 1 appeared 1 time. We have to count the number of times that 2 appeared. So we have 1, 2. 2 only appeared 1 time, which means that 2 will have a frequency of 1 also. That'll go right there. Now we have to count the number of 3s. We have 1 3 in the data set, which means that 3 has a frequency of 1 also. And now we have to count the number of 4s. We have 1, 2 4s in the data set. So since we have 2 4s, the frequency of 4 is 2. This is our second frequency distribution table. It just shows each value in the X column. Each value that appeared is in the X column, and the F column just shows how many times each value appeared. Now let's go over a few important points about frequency distribution tables. One important point is that the numbers in the X column have to be in order. Remember that, well, this is the table that we created with our first data set. So notice how we put the numbers in the X column in order. It goes 1, 2, and then 3. This is the correct way to create a frequency distribution table. It wouldn't be correct to create it this way because the numbers in the X column are out of order. And when you put the numbers in the X column out of order like this, the table doesn't look very organized and it's difficult to read. That's why you want to create a table like this, in which the numbers in the X column are in order. Here's another point about frequency tables. Values with a frequency of 0 are included only if they are somewhere between the lowest and highest values. And I'll show you an example of what I mean. If this was our data set here, and we had 1, 2, 3 3s, and 1 4 in the data set, and we didn't have any 1s in the data set, we actually wouldn't include 1 in the X column. We would leave this off, and this would be our entire table right here. So the reason why we wouldn't include 1 in the X column is because 1 is below the lowest value. In this data set right here, 2 is the lowest value that appeared in the data set. So we wouldn't have to include 1 because that's below our lowest value. if this was our data set right here, and we had 1, 1, 3 2s, and 1 3, then 3 would be our highest value, which would mean that we wouldn't have to include 4 in the x column. So if 2 is the lowest value in the data set and 1 never appears, you don't have to include 1. It's below the lowest value. If the highest value in the data set is 3 and 4 never appears, you don't have to include 4 because it's above the highest value. But if we had a data set like this, in which we had 3 1s, 1 3, and 1 4, but no 2s, we would have to include 2 in the x column, because 2 is actually between our lowest and highest values. Our lowest value is 1, and our highest value is 4, and 2 is in between the highest and lowest values. So since this value of 2 is between the lowest and highest values, it has to be included in the x column, even if it has a frequency of 0. The reason why is because you don't want the x column to skip over numbers. You don't want the x column to go 1, 3, 4, because it makes the table harder to read when it's skipping over numbers. Also, if too many different values are possible, it's better to create a grouped frequency distribution table. And I'll explain what a grouped frequency distribution table is. When you create a grouped frequency distribution table, the x column doesn't have individual values anymore. Instead, the x column has groups of numbers like 10 to 19, 20 to 29, 30 to 39. If I was asking a group of people for their ages, and I know that there's many different ages that could end up appearing in my data set, then I wouldn't want to list every possible age in the x column, because my x column would be very long. Instead, I would want to create groups of ages like 10 to 19, 20 to 29, 30 to 39, so my x column isn't quite as long. Here's an example. I ask 4 random people for their ages, and I get 2 people in their 20s, 1 person in their 40s, and 1 person in their 50s. If I tried to list out every value in the x column between my lowest and highest numbers, I would have a very long x column, because my lowest value is 25 and my highest value is 52. If I listed out every value between 25 and 52 in my x column would include about 27 numbers, and it would be too long. Also, most of the frequencies in the f column would be zeros, because most of the values in this data set, most values between 25 and 52 don't appear at all. I only actually recorded 4 different values, or 4 different ages. So it would be much better to create a grouped frequency distribution table like this that shows groups of numbers inside the x column instead of individual numbers. This is showing that in my data set, 2 people were in their 20s, no people were in their 30s, 1 person was in their 40s, and 1 person was in their 50s. So there's 2 20s right here. That's why this f is a 2. There's no 30s, which is why this is a 0. There's 1 40, which is why this is a 1. And there's one number in the 50s, which is why this is also a 1. Remember that if you have a frequency of 0 that's somewhere between the lowest and highest values, that frequency of 0 has to be included. So if I had let's say I had two people in their 30s, one person in their 40s, and one person in their 50s, and no people in their 20s. Well then, this wouldn't be needed. I could just cross it off because it has a frequency of 0. But the fact that I have people in their 20s and all the way up to people in their 50s means that this has to be included, even though it has a frequency of 0. Remember, you don't want the x colon to be skipping over values. I wouldn't want this to skip from 20s to 40s to 50s. So in a group frequency distribution table, each group of numbers is called a class interval. So each of these groups that I have in here is called a different class interval. 20 to 29 is a class interval. 30 to 39 is a class interval. And these are the other two class intervals. So we're just going over some vocabulary right here. The number of possible values that are covered by each class interval is called a class width. Let's look at an example of a class width. First, let's talk about how there's a formula for the class width of a table, and that the formula is just subtracting the upper boundary by the lower boundary and adding 1 to the answer. So this formula will make sense once we look at an example. Let's go back to our first table right here that we looked at earlier. Notice how each of these class intervals goes up by 9. So 20 goes up to 29, 30 goes up to 39, and 40 goes up to 49. Let's think about how many different numbers are covered inside each of these class intervals. Well, there's actually 10 numbers in between 20 and 29, because 20 is the first one, so 20, 21, 22, 23, 24, that's 5 numbers, and then 25, 26, 27, 28, 29 is another 5 numbers. There's actually 10 numbers in between 20 and 29. I know it seems like there should be 9 numbers, but there's actually 10 because 20 is the 10th number. There's also 10 numbers in between 30 and 39. And there's 10 numbers between 40 and 49, and 10 numbers in between 50 and 59. Since each class interval covers 10 numbers, you would say that this table has a class width of 10. Now I've helped you understand the idea of a class width. Now let's talk about how the class width can be found with using a formula. So I said that to get the class width of the table, you have to pick a certain class interval. You can pick any class interval you want to. I might decide to pick 20 to 29 as my class interval. Then I subtract the upper number of the interval by the lower number of the interval, and I add 1 to my answer. Let's try that. So I'm taking this upper number of 29, subtracting it by the lower number of 20, and adding 1 to the answer. 29 minus 20 is 9, and 9 plus 1 is 10. And like I said, this table has a class width of 10 because each class interval covers a span of 10 numbers. And when I say that each class interval covers a span of 10 numbers, I don't mean that 10 20s appeared in the data set and 10 30s appeared in the data set. What I mean is that there's 10 possible numbers inside of this class interval. There's 10 possible numbers that could have appeared, and this class interval also has 10 possible numbers that could have appeared. Um, now let's try to figure out what the class width is in this table. Just like before, let's try to find the class width just by thinking about what the class width should be, and then we'll use a formula next. So here the first class interval is 0 to 19. Well, we know that 1 to 19 is 19 different numbers, and that 0 would be a 20th number, which means that there's 20 numbers in between 0 and 19. There's also 20 numbers in between 20 and 39, because it's, well, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29 will be 10 numbers, and 30, 31, 32, 33, 34, 35, 36, 37, 38, 39 would be 10 other numbers. So there's 20 numbers inside of this class interval too. There's also 20 numbers in between 40 and 59. So in this table, each class interval covers a span of 20 numbers, which means that this table has a class width of 20. And that can also be found by just picking an interval, by picking a certain class interval and subtracting the upper number by the lower number and adding 1. So 19 minus 0 is 19. And then 19 plus 1 is 20. And like I said, this table has a class width of 20. And in this table, the class width is larger because notice how these class intervals are covering more numbers than they were before. So actually, each class interval in this table covers a span of 50 numbers, because there's 50 numbers in between 0 and 49, and 50 numbers between 50 and 59. And just like before, we can use the formula. I just took the first class interval, I subtracted the upper number of 49 by the lower number of 0. 49 minus 0 is 49, and then 49 plus 1 is 50. The class width is 50. It's possible to take a frequency distribution table and change it into a bar graph called a histogram. And a histogram has certain advantages over a frequency distribution table. The main advantage of a histogram is that it's better at showing something called the shape of the data, or the shape of the distribution. And I'll explain to you what it means for a data set to have a shape. First, let's take one of our frequency distribution tables and change it into a histogram, and then we'll actually get to see how the data set has a certain shape to it. So we'll take this data set that we looked at earlier, and this frequency distribution table of the data set over here, and we'll change the table into a histogram. On this screen, this table is just showing the frequency of each value that appeared in this data set. So this table and this data set go along with each other. Now we're going to change the table into a bar graph. Called a histogram. And each bar in this histogram is just showing the frequency of the value that's below it down here. So we can see that this value of 1 has a frequency of 2 because there's 2 1s in the data set, 1, 2. This value of 2 down here appeared 3 times because 1, 2, 3. So that's why this So this answer of 2 has a frequency of 3. 3 appeared 2 times in the data set, so 3 has a frequency of 2. So each of these bars is just the frequency of the value. There's 2 1s in the data set, which is why this bar goes up to the second tick mark. There's 3 2s, which is why this value goes up to the third tick mark. And there's 2 3s, which is why this bar goes up to the second tick mark also. A frequency distribution table can be changed into a type of bar graph called a histogram. I'll explain how to do that in just a second. First, I wanted to mention that the main advantage of a histogram over a frequency distribution table is that a histogram is better at showing the shape of the data, or the shape of the distribution of the data. Any data set that's quantitative, meaning it's made up of numbers, has a shape to it. It piles up where most of the values are, and then it trails off once you get to parts of the number line that have fewer and fewer values. For example, a bell-shaped curve goes along with a data set that has fewer lower values and fewer higher values, and most of the values piling up in the middle. So a histogram is better at showing the shape of the distribution of a data set. And I think it'll make more sense what a distribution means once we go over a couple of examples. So here's our first example. We have this data set right here. We've recorded data from 7 people. Each of these numbers can be whatever you want them to be. They could be the number of children that each person has, maybe. Here we have a frequency distribution table that summarizes this data set. This table is just showing that 2 people said 1, 3 people said 2, because we have 3 3s, and 2 people said 3, because there's these 2 answers down here. So 1 appeared 2 times, 2 appeared 3 times, and 3 appeared 2 times in this data set over here. We can change this frequency distribution table into a histogram. We just have to replace each of these numbers in the F column with a bar that shows the frequency of the value in the X column. So remember that before we look at this histogram, remember that the 3 numbers in the X column are 1, 2, and 3, and that the frequencies are 2, 3, and 2. Now, in this graph, we can see that we still have the 3 numbers that were in the X column, 1, 2, and 3. And now these bars are showing the frequencies of the three values. Remember that 1 had a frequency of 2 because there are 2 1s in this data set. Since 1 has a frequency of 2, this bar goes up to the second tick mark. This bar is going up to the second tick mark just because we have 2 1s in the data set. Remember that 2 had a frequency of 3 because there were 3 2s in this data set right here. Since 2 has a frequency of 3, this bar goes up to the third tick mark right here. And remember that 3 had a frequency of 2 because there are 2 3s in this data set. Since this number 3 has a frequency of 2, its bar goes up to the second tick mark. So basically what these bars are showing is that we have 2 1s, 3 2s, and 2 3s in the data set. The 2 numbers that appeared less often have shorter bars, and the value that appeared the most often had the tallest bar. And notice how this histogram is showing the same information that we saw in the table. In this table, the frequencies were 2, 3, and 2. And in this histogram, the frequencies are 2, 3, and 2. And now we can also see that this data set has a certain shape to it. It's not really bell-shaped, but it's sort of bell-shaped because it starts off at a short area. It starts off with a short bar right here. It goes up to a taller bar, and then it goes back down to a short bar again. So it goes up and then it goes down. We can see this shape if we outline this histogram with a curve. So here this green line sort of shows the shape of this histogram right here, how it rises and then it falls. Here's another data set, and here's the table that summarizes the data set. And once again, we'll change this table into a histogram. We can see that this table is showing that we have 3 1s, 2 2s, 1 3, and 1 4 in the data set. So 1 appears 3 times, it has the largest frequency. 2 only appears 2 times, so it has a lower frequency. And 3 and 4 have the lowest frequencies because they only appear 1 time. So as the numbers are getting larger, the frequencies are getting smaller. So you can probably imagine that the histogram is going to peak at the low end because the tallest bar will be at 1, and then the bars will get shorter and shorter going to the right because these frequencies are dropping down. And that's what the histogram looks like. 1 has the largest frequency because it's a frequency of 3. 2 has a lower frequency, and 3 and 4 have even lower frequencies. So we can see a shape that's peaking at the left end and then trailing off toward the right, like this. Because as we're going up to higher and higher numbers, the numbers are appearing less and less often. So here we have this type of a shape that suddenly peaks at the left end and then trails off gradually toward the right as the numbers appear less and less often. This type of a shape actually has a name that we'll get into later. When you see this type of a shape, you would say that the data is skewed to the right. It's skewed toward the right because it gradually trails off toward the right end. Now let's look at this data set right here. Now we have a grouped frequency table that has these class intervals instead of just values in the x column. But notice how the frequencies are 2, 2, and 3. We have 2 20s, 2 30s, and 3 40s. That means that the bars in the histogram will be 2, 2, and 3, just like they were in the table. All this is showing is that we have 2 20s up here. We have 2 30s right here, and we have 3 40s right here. Since we have 2 20s, this bar goes up to the second tick mark. Since we have 2 30s, this bar goes up to the second tick mark. And since we have 3 40s, this bar goes up to the third tick mark. So that the value that appears the most often has the tallest bar, and values that appear less often have shorter bars. Here we have a different type of a shape. Here we have a different type of a shape because it peaks at the right end and then trails off toward the left. This type of shape also has a name. When the histogram peaks at the right end and then trails off toward the left, you say that the data is skewed to the left. It's skewed to the left because it's gradually trailing off toward the left end. So I've already talked about the names of a couple of different shapes. Now let's go over some other types of names that the shapes can have in a histogram. If the histogram has a bell shape that peaks in the middle and then gradually trails off in both directions, you say that the data has a normal distribution. And a normal distribution is just a technical word for a bell-shaped curve. We've all probably heard of what a bell-shaped curve means. It's just a shape that looks like a bell that goes up, peaks in the middle, and then goes back down again. So this is a normal distribution or a bell-shaped curve, or it's my best attempt to draw a picture of a normal distribution. It goes up gradually and makes a bell shape, and then it goes back down gradually again. This is the type of shape that a data set has when you have few people with really low values and few people with really high values, and most people with values that are median or in the middle right here. If a certain class takes an exam and very few people get D's and F's, or very few people get really low exam scores, and really few people get really high exam scores, and most people get exam scores somewhere in the middle, then the exam scores of the class have a normal distribution, or at least a roughly normal distribution. Also, a data set that peaks too far to the left to be normal, or peaks too far to the right to be normal, is called a skewed distribution. And so the skewness of a data set refers to the extent to which the data set peaks too far to the left to be normal, or too far to the right to be normal. Let's look at some examples. If the histogram peaks too far to the left to be normal, and it gradually trails off toward the right, then you would say that the data is skewed to the right, like I said earlier. And the technical word for that type of shape is called a positively skewed distribution, or a positive skewness. So here's a data set that's skewed to the right, or positively skewed, where it peaks to the left of a normal curve and then gradually trails off toward the right. The reason why I put this red arrow here is to show how it's trailing off toward the right end. That's why you say it's skewed to the right. And to help you understand why it's called a positive skewness, you could think that I would think about how it's trailing off toward positive numbers, because the right end is the positive end of the number line. So just think that it's trailing off toward the right end, and it's also trailing off toward positive numbers. If it peaks at the right end and it trails off toward the left, like this, it's the opposite type of shape, which is called a shape that's skewed to the left, or a negatively skewed shape. And like I drew this arrow to show how it's trailing off toward the left end. That's where this word skewed to the left comes from. And it's a negative skewness because, you could think of it as how it's trailing off toward negative numbers. That's one way to think about it. So this type of a shape, a negative skewness, peaks too far to the right to be a normal curve, and this shape that's a positive skewness peaks too far to the left to be a normal curve. You have to remember that skewed to the left doesn't mean it peaks at the left end, and skewed to the right doesn't mean it peaks at the right end. Skewed to the left means that it actually peaks at the right end and trails off to the left, and skewed to the right means it actually peaks at the left end and then trails off toward the right direction. So these names can be a little bit misleading because it's not named after the side that it peaks on, it's named after the side that it trails off toward. Now we talked about the skewness of a data set, now we'll talk about the kurtosis of a data set. The skewness of a data set has to do with whether it peaks to the left of a normal distribution or to the right of a normal distribution. The kurtosis of a data set has to do with whether it peaks too high to be a normal distribution or too low to be a normal distribution. And there's two types of kurtosis that you can see in a data set. A data set that's shorter and flatter than the normal distribution is called a negative kurtosis. So a data set like this that has a shorter and wider peak than the normal distribution has is called a negative kurtosis. Negative kurtosis is flattened out more like a pancake. The opposite is a positive kurtosis, which is when it has a taller and narrower peak than the normal distribution, like this, where the peak is more narrow and it's also going up higher than the normal curve does. So a negative kurtosis is shorter and wider than a normal curve. A positive kurtosis is taller and narrower than the normal curve. This one has this wide and short peak. This one has this tall and narrow peak. You can imagine if this distribution, if this normal distribution was made out of Play-Doh and I pushed down on the top and flattened it out, I would get a negative kurtosis. If I pushed in toward the sides and I made this peak and I made the Play-Doh go up taller and narrower, it would become a positive kurtosis. So a normal distribution is halfway between a negative skewness and a positive skewness, because the normal distribution doesn't peak too far to the left or too far to the right. It peaks right in the center. A normal distribution is also halfway between a negative and a positive kurtosis, because it peaks somewhere between this and this. So the reason why I put these in the center, like I did here, is to show that the normal distribution is halfway between these two shapes, and it's also halfway between these two shapes. Since it's halfway between the negative and the positive skewness, you would say that a normal distribution has no skewness. And since a normal distribution is also halfway between a negative and a positive kurtosis, you would say that a normal distribution has no kurtosis. So a normal distribution actually has no skewness and no kurtosis. It's the absence of skewness and kurtosis. So no skewness and no kurtosis. And we're not going to get into the formulas for these values right here, but I just wanted to show you that there are values that can be calculated to measure the skewness and kurtosis of a data set. A skewness value can be calculated to show the skewness of a data set, and if the skewness value comes out to a negative number, it means that you have a negative skewness. It means that the data is peaking at the left and trailing off to the right. I'm sorry, I didn't say that right. If the skewness value comes out to a negative number, you have a negative skewness, which means that the data is peaking at the right end and trailing off to the left. If the skewness value comes out to a positive number, you have a positive skewness, which means that your data set is peaking at the left end and trailing off to the right. If the skewness of the data set comes out to 0, you have no skewness at all. It means that the data peaks right at the center. And the further the skewness value comes out below 0, the more dramatic of a negative skewness you have. And the further the skewness value comes out above 0, the more dramatic of a positive skewness you have. So it's more dramatic negative and more dramatic positive as you go out further from 0. And actually, well, I said that if it comes out to 0, there's no skewness at all. But if the value comes out somewhere between -1 and +1, there's roughly no skewness, which means that the histogram peaks at least roughly in the center. If it comes out below -1, it's a considerable negative skewness. And if it comes out above +1, it's considered a considerable positive skewness. So what we see here are just the guidelines for interpreting the skewness value. You can also calculate a kurtosis value. Just like the skewness value, a kurtosis value that's negative shows that the data has a negative kurtosis, which means that it's more flattened out. A kurtosis value that's positive out here means that the data has a tall and narrow peak, and it has a positive kurtosis. So if your kurtosis value is negative, you have a negative kurtosis. If your kurtosis value is positive, you have a positive kurtosis. That makes sense. If your kurtosis value comes out to 0, you have no kurtosis at all, which means that the data peaks right at the center. It doesn't peak too high or too low. It peaks right where a normal curve peaks. And just like with the skewness value, a kurtosis value further below 0 means you have a more dramatic negative kurtosis. It means that the data is more dramatically flattened out. A kurtosis value further above 0 means you have more of a dramatic positive kurtosis, meaning that the data has even more of a tall and narrow peak. But just like before, with the skewness value, a kurtosis value between -1 and +1 means that you have roughly no kurtosis in your data. If your kurtosis value comes out between -1 and +1, it means that your data isn't really too flat or too tall. It's about in the center, and it has roughly no kurtosis. So if the value came out a little bit below 0, it means that your data is a little bit flat. It's a little bit flatter than the normal curve. If it comes out a little bit above 0, then your data is a little bit too tall and narrow to be perfectly normal, but it's still pretty close to normal. So anytime the value comes out in here, it means that you don't really have a dramatic negative or positive kurtosis. It's basically roughly no kurtosis. And just like with the skewness value, this is considerably negative, and this is considerably positive. So the kurtosis value has the same guidelines that the skewness value has. So since a data set that's perfectly normal has no skewness and no kurtosis, it makes sense that a normal distribution would have a skewness value of 0 and a kurtosis value of 0. If you take a data set and you calculate the skewness and kurtosis, and they both come out to exactly 0, then you have a perfectly normal distribution. But no data set in the real world is actually perfectly normal. A lot of data sets will be close to normal, and these values will come out close to 0, but no data set is perfectly normal. So these two values will never come out to exactly 0. A lot of data sets in the real world that come out roughly normal are things like height and IQ, or scores on personality tests. Those types of scores tend to follow a normal curve because you tend to see more people in the middle and fewer people at the extreme ends of the number line. And remember how a skewness value between -1 and +1 is roughly no skewness, and a kurtosis value between -1 and +1 is roughly no kurtosis. So if both values come out between -1 and +1, you have both roughly no skewness and roughly no kurtosis, which means that your data is roughly normal. If you want to be able to decide whether your data is roughly normal, you can calculate the skewness and kurtosis values and check to see if both values come out between -1 and +1. If they do both come out between -1 and +1, you can then say that your data follows a roughly normal distribution. So one way to decide whether your data is normal is to create a histogram and to look at the shape of the histogram. But um, that requires the researcher to make a judgment call about whether the data looks normal, and it's a little bit subjective. This way of deciding whether the data is normal is more objective because you're actually depending on numbers that have been calculated to measure the exact amount of skewness and kurtosis in the data set. But it's not creating a histogram and looking at the data isn't a bad thing to do, even though it is a little bit subjective. Actually, a good approach to judging whether your data is normal is to both create a histogram and calculate these two values, and use all of the information to decide whether the data appears to be normal. So here's an example I created to show you the skewness and kurtosis values of a data set. Here we have one column of data. It can be whatever you want it to be. Like I said, these could be just the number of children that 10 people have. Maybe these are just the answers to a survey in which I asked 10 people how many children do you have, and I recorded their answers. This could also be the answers to a survey in which 10 people told me how many children they have. But notice how these two data sets are different, because here 5 appears the most often, which is why we have this tall bar right here. And these lower numbers are showing up less and less, which is why these bars are dropping. Here, the lowest value of 1 appears 4 times, so we have this tall bar going up to 4, and these higher values are appearing less and less often. So this shape is the opposite of this shape. This one is negatively skewed, this one is positively skewed, and they're actually the mirror images of each other. So what's going to happen is when we calculate the skewness and kurtosis values, when we calculate the skewness value of this data set and the skewness value of this data set, they'll both come out to the same number, but the sign will be different. And we can see that happened because this is a negative 0.998, this is a positive 0.998. If two data sets are the mirror image of each other like this, the skewness number value of this data set will be the opposite of the skewness value of this data set. So since these are both a 0.998, what that means is that the skewness of these two data sets is equally dramatic. This data set has the same amount of skewness that this data set has, but they just have opposite types of skewness. The kurtosis value is equal, but they're both negative 0.187 because, well, this data set, the flatness of this data set and the flatness of this data set are the same. Which is why they have the same amount of kurtosis. And also, remember that the normal distribution has a skewness and kurtosis of 0. Here's one other example. This time I want us to focus more on kurtosis than skewness. Notice how this one is really flat, so it should have more of a negative kurtosis value, because it's more of a negative kurtosis. And that's actually what happened. It has a kurtosis of negative 1.17, which is actually below negative 1, which means it does have a considerable negative kurtosis. But the skewness value is really close to 0, and so it has almost no skewness at all, and that makes sense because, well, it's peaking right at the center, or at least close to the center, so it doesn't have very much skewness. Let's look at the skewness and kurtosis values of this data set. The kurtosis is a little bit positive because it does have this tall and narrow peak this time. And the skewness is still not very dramatic. It's between -1 and +1, which means roughly no skewness. And by looking at the data, we can see that it does have roughly no skewness because it does peak pretty close to the center. It's not skewed really far one way or the other. So we've talked about skewness and kurtosis. One last point that we want to make at the end of this video is that if a data set has a normal distribution and it has a bell-shaped curve, the mean, median, and mode are all equal. They're all the same number. If the data is positively skewed, the mean is above the median, and if the data is negatively skewed, the mean is below the median. And I'll show you some diagrams of that. If a recorded set of numbers, meaning a column of data, has a normal curve, then the mean, median, and mode of that column of data are all the same number. If a recorded column of data has a positive skewness, meaning the column of data has a lot of low numbers and not very many higher numbers, then the mean will be above the median, like this. If a column of data has a negative skewness, which means it has a lot of high numbers and fewer low numbers, and the numbers are piling up at the high end, then the median of that column of data will be higher than the mean of that column of data. So you can think of it as the mean is being pulled toward the direction of the skewness. When it's skewed to the right, like this, the mean is pulled toward the right end. When it's skewed to the left, the mean is pulled out toward the left end. Let's look at one example of that. So this column of data right here is skewed to the left. It's negatively skewed because it has a lot of high numbers and not as many lower numbers. So we can see that the median is above the mean, like we talked about. This column of data is positively skewed because it has more higher numbers and fewer lower numbers. And the mean of this column of data is above the median, like we talked about. So when you have a negative skewness, the mean is below the median. When you have a positive skewness, the mean is above the median.